Okay, so this is another static equilibrium problem. Yeah, so nothing. So the previous one wasn't static, but very similar analysis to this problem. This one's a little. I would say the torque piece is a little easier than the previous problem. So if I think about the sign just a rod, it's a little bit easier to analyze. This is my pivot point. So in terms of torque, if I make this the pivot, so another way to, I could do this exact same context and just ask you for the tension in the rope, for instance. That would be an easier problem than to have to go to the following steps about the bolt. So no harm looking at this question. The easier version would be just ask for the tension in the string, assume everything's at rest. So there's an mg force here in the middle, causing a clockwise torque. And then there's color here. There's a tension force here, causing a counterclockwise torque. So for the net torque to be 0, the torque of the tension has to be equal to the torque of the weight. So let me do this down here. So torque tension has to be equal to torque mg in order for everything to be balanced. So that's the tension force here, and this angle is 20 degrees. So I'm looking for the perpendicular components that will be assigned in this example. So t sine of 20 degrees times its distance from the pivot, which is 3.2 meters, is equal to mg times its distance, and it's perpendicular already. So 16 kgs times 9.81, 9.8 meters per second times 1.6 meters. So if you divide this thing here on the right by sine 20 times 3.2, I believe the tension is 230 newtons. And because of the symmetry in this problem, that's actually the answer. But just to show you the steps, if there's not like a complete symmetry in the problem, how you would solve the problem for a slightly more complex question. Any questions so far? So that could be just a valid exam question, just solve for the tension. So then what I would do, I would consider then, figure the bolt is consider the forces that are on the, if I treat it as a sort of a point diagram now. So I've got a 230 Newton force here, which I can decompose into x and y components. So if you do 230 times the cos of 20 degrees, the tension x is 215. And the tension y is 78.4. It also has a weight force of m times g, so 16 times 9.81. So that's the, did I do that? Yeah, 157. So they're the two forces outside of the bolt. So the bolt must exert forces such to balance these forces. So the bolt, in order to balance, since the weight has no x component, the bolt force, I'll do here in pink, has to have an x component of 215 newtons. We've got 78.4 upwards due to the tension, but we've got a large 157 newtons downward. So the bolt has to have a y component that balances these two. So let's take the difference between those two. Again, it ends up being 78.4. So there is symmetry in this problem, but this is the general solution. So then if you didn't know this, you could solve for the bolt force, F bolt, as the square root of 78.4 squared plus 215 squared, which gives you 230 newtons. So I think we did a similar problem for the lower back, like finding the force that's on the bottom of the spine when you're doing a deadlift. Similar analysis. So first using torque, and then using Newton's law so that there's no net force and there's no net torque on this sign. Question?
Can you just restate again how you got that the force pointing upward is 78.4? Like I assume that you need the x component balancing the 215. Yeah, but so if you know you have the weight force 157 pointing down, how do you get to the other two components?
So the one in green here comes from just doing 230 times the sine of 20. So, and then this other setting comes from the subtraction of these two. So I need the 2 up y's equal to down y. So if I only have 78.4 upwards and 157 downwards, once you subtract those, you end up the same. If you don't take any, so it's 156.8 is the weight force if you do an extra decimal. Okay.
So the coordinates 0, there's like a net force on the object. It's like not rotating, it's like moving.
The question is if there's a net torque is 0, but there is a net force, there can be no alpha. It can be, in a sense, it could be rotating at a constant speed, but there's no angular acceleration, and it would have a linear acceleration. So no net torque means no alpha. Does not mean it's not rotating. It's just like net torque does not mean at rest. No, net force is 0 doesn't mean at rest. It just means constant speed. Okay.